is the data is the data that we're using to train the model. Okay, so as I mentioned before, each data record is called simple, and we have also the training set is the data set that we're using for the training process. And we have the test set is the the data set that we're going to use for testing. Okay. And remember when we were talking about the data set, we said that we have to devise our data set into training set and test set and sometimes validation set. Okay, so I mentioned the difference between test set and validation set. Can you please tell me what is the difference?
Validation set is used during training and test set after training.
Perfect. So, um, and what is the importance of using validation sets?
We
It is
can
used to adjust the model.
oh, sorry.
You can use that reaction button to raise your hand. So whomever do it first will get to talk first. Can you see it?
Mm. Yes.
Okay, perfect. So Arasli.
Yes, I just was to say that the performance is the important technique of validation.
The
It
performance?
measures the accuracy and performance of the model.
Okay, so you measure, sorry, I didn't get what you mean. Can you please repeat what you said?
Yes. Yes. You asked for the difference between validation and test, right?
Yes.
Okay, yes. I remember that it was something about measuring the performance of the model,
Yes.
of the loss accuracy and that stuff.
Yes, so I was saying that validation set. Why do we use? What is the importance of validation set? I was actually I mentioned that in using validation set we don't have to. Okay, Cheryl Melara.
I guess to make predictions with
No,
accuracy.
no, we actually don't. We actually use the validation set, for example, not just to wait until the whole training finished to know actually what is the performance of our model. Okay, so we use it in the training while the model is training instead of after the training, and then we evaluate our model. We can actually have the opportunity to see how is the model doing while training, and we can stop training and adjust the parameters, for example, or so. Now do you see my point?
Yes.
Okay. Everyone?
Yes.
Okay. Okay, perfect. So, okay, so test sets. Now we'll move on to I think that is not changing. I will reshare my screen. Okay, now can you see it?
Yes.
Okay. So here, can you see the check-in data overview? So here in the data overview, this is a typical dataset form. So as you can see here, we have three features: area, school districts, direction, and the target variable, which is the label, the house price. And we have the training set from 1 to 4. So we have 4 rows for training set and 1 row, for example, for test set. This is just an example. So can you tell me what is the problem that we're trying to solve in this slide?
Price? The house
The,
price?
the house price. What we are trying to do? Is it a classification or a regression problem?
I'm sorry.
Is it a
It's a
classification or a regression
regression.
problem? A
Regression.
regression. Yes. We are trying to predict the house price based on the direction, school districts, and area. Okay. So, so now let's move on to the data processing. Data processing, data is crucial to models, so it is the scaling of model capabilities. Without good data, there is no good model. That's true. So when we are dealing with machine learning projects, we have real world data. Real world data typically is not ready to be used. So for example, in the platforms like Kaggle, they have multiple data sets that are ready to use. But in real world data, normally it's a challenge to actually have a data, or if you're lucky, super lucky to have a data that is ready actually to be used right away. So there might be missing values or incorrect types in the dataset that we get. Uh, these rawness of the data needs to be dealt first so that the ML model or the ML algorithm can be applied on it. So this is a common problem that all data related professionals have to face in daily basis. Okay. Um, Now the process of dealing with unclean data and transform it into more appropriate form for modeling is called data pre-processing. So this step is a mandatory step in machine learning process. And one of the most common process of data cleaning or data pre-processing is we have data cleaning, we have data dimension reduction, we have data normalization. And in data cleaning, we deal with, for example, missing values. So basically, there are two ways to handle missing values. Either we remove the rows with the missing values, or we impute missing values. So when it comes to removing the rows, it is the simplest strategy ever. So, and it is easy to execute. But however, when we are trying to impute missing values or replace the missing values, it is a little bit complicated. So we can replace the missing values using some rules. For example, the constant value uh, that has meaning within the domain and different from other data like 0 or -1. So either we replace the missing values with 0, for example. We also tend to use another strategy or another method, which is central tendency of data. For example, the mean, the median, or mode. So we can replace the missing values with the mean or the median or the mode. And another method that we use is predictive values. So we actually try to predict the missing values, and we estimated them based on other data. Okay. Uh, okay, so another technique of data pre-processing, as mentioned in the slide, we have data dimension reduction. So data dimension reduction, do you know any algorithm? Maybe you come, if you have a background in mathematics, do you know any algorithm that does that? Dimension reduction in statistics.
Vectorization can be.
Um, no, I was looking for a particular one, popular technique we use. PCA. Did you hear of PCA? Principal Component Analysis. Yes? Okay,
I
so
never
you have,
heard of it.
okay, so this is a popular technique for dimensionally to reduce the dimension. Okay, so if I'll give you an example why we actually do this data dimension reduction technique. Most importantly, because more input features often make a predictive modeling task more challenging to model. So, as I mentioned before, for example, if you have an Excel file and we're trying to predict just one target variable based on multiple features, let's say million or billions of features. So, the dimension of the problem is going to be complex. Okay. So that's why we think about data dimension reduction. And we generally refer to as the curse of dimensionality. And one of the most popular techniques that we use for dimension reduction is PCA, principal component analysis. You can note this, so you can actually Google it afterwards to just have an overview on how it works and what it is. Because I think we cannot cover all of the terms in details. So I think it's gonna be good if you have some free time to actually look it up. Okay. Okay, and
Okay, okay, thanks.
okay, and the third technique is data normalization. We actually try to normalize the data to reduce noise and improve model accuracy. We've done this in with the first exercise. We normalize the data between 0 and 1. Okay. Okay, so this is a statistic on data scientists' work in machine learning. Remember, I mentioned that 80% of the work in machine learning projects takes a lot of time in cleaning, sorting the data, collecting the data sets. So as you can see, 60% for cleaning, sorting the data, and 19 for collecting data sets. And the rest is just 4%, 5%, 3%. Okay, so for data cleaning, I'm going to jump to, okay, perfect. The data cleaning, there are multiple. Okay, this is a great example of dirty data. So we can see here we can have duplicate items or duplicate rows. We can also have incorrect formats. As you can see here, we have one type of format, and we can have rows with different type of formats, not the same type. We can have misspelling, Italy. Um, attribute dependency value that should be in another column here, for example. So Italy, this is a country, not a city. We can have missing values and invalid values, etc. So these are some of the challenges that we face daily with the real data. Okay. And we have, of course, to solve all this before going to the process of training the model. So this is the phase of pre-processing. Okay, so now this is why we actually need the feature selection. So feature selection methods are intended objective of feature selection is to reduce the number of input variables to those that are believed to be most useful to a model in order to predict the target variable. So some predictive modeling problems have a large number of variables that can slow the development and the training of models, and it requires a large amount of system memory, as I mentioned before. We can have millions of features or millions of variables. So that will be a complex problem to solve. And additionally, the performance of some models can degrade when including input variables that are not relevant to the target variable. Okay, so one way to think about feature selection method, we can think about them into methods that are in terms of supervised and unsupervised methods. Okay, so the difference has to do with whether the features are selected based on the target variable or not. Unsupervised feature selection techniques, they ignore the target variable. So whenever you have a method in feature selection that ignores the target variable, this is an unsupervised method in feature selection. And whenever we take into consideration the target variable, we are talking about a method a supervised method in feature selection. Okay, so the unsupervised feature, as I said, the selection, it ignores the target variables such as methods that remove redundant variable using correlation. So we basically use correlation in order to remove the redundant variables. Or what I mean by redundant variables is that variables that add the same information. Okay, so if we have, for example, two variables that are highly correlated, that means that they actually give the model the same information. We actually drop one of them. Okay, so we delete one of them, we drop one of them, or we ignore one of them, and we use the other one because they add the same information to the model. Okay, so this is when we're talking about unsupervised feature selection. Now, okay, I will add someone, I guess. Okay. So now when we were talking about unsupervised feature selection, we said that it ignores the target variable, and we use method that remove redundant variables using correlation. Okay. Now we were talking about supervised feature selection techniques. It actually uses the target variable. Okay, so this is the main difference. We have multiple methods for each type, and I'm going to actually go to the next slide to actually show you. So in when we are talking about supervised method, there is filter and there is wrapper. Okay, and there is another type. Okay, so this is filter and wrapper and embedded. So these are feature selection methods supervised. Perfect. And in unsupervised, we only have the method correlation. We use correlation to drop the variables that actually add the same information to the model. Is it clear? Do you understand the difference between the two?
Yes, it is clear.
Okay. Okay, now let's go to the first method. Okay, can someone of you just summarize what I said about supervised and unsupervised methods in feature selection? And what are the supervised feature selection methods? Yes? Okay, so you didn't get what I was talking about? Should I repeat?
Yes, could you please repeat?
Okay. Okay, so please stop me if you actually didn't understand what I was talking about, so I can explain it to you in a better way. So I was talking about feature selection. So you understand the meaning of feature selection method or the importance of feature selection method? Yes?
Yes.
Okay, so just to sum up, we want to use the feature selection method to reduce the number of features and to those that are believed to be the most useful to the model, to our model, in order to predict the target variable. Okay, now there are two types of feature selection methods. We have supervised and we have unsupervised methods. In supervised method, we have filter, we have wrapper, and we have embedded that we're going to see. So we have three methods in supervised. And supervised in unsupervised method, we have only one method, which is to eliminate the variables that actually add the same information to the model using correlation. So we eliminate the highly correlated variables to each other. We drop them, okay? And in supervised learning, in supervised methods, I said we have three. We have embedded, we have wrapper, and we have filter, okay? So we have three. And the difference between the two, supervised and unsupervised, is that when we are talking about unsupervised, we ignore the target variables. Why? Because we actually remove the redundant variables using correlation just between them. We don't see the correlation between the variables and the target variables and how it goes, okay? We only care about the correlation between the features, okay? Instead, in the supervised learning or in the supervised methods, we care about the correlation. For example, in the filter method, we care about the correlation between the variables and the target, and based on that, we make decisions. Is it clear now?
Yes, yes, it's clear.
Okay, so what is correlation? Could we have any idea what is correlation? Because I mentioned correlation, I think I didn't define it, so they didn't in slides anyway, but it's important to know what is correlation. What is the meaning of correlation?
It's when two variables are related.
Exactly. So correlation exactly explains how one or more variables are related, as you mentioned, to each other. So correlation is a statistical technique which determines how one variable moves and changes in relation with the other variable. So it gives us the idea about the degree of the relationship of the two variables. For example, we can let's think of an example of number of testing vs on number of positive cases in COVID-19. Okay, so the number of people that got tested and the number of positive cases in COVID-19. These two features or these two variables are correlated. Okay, so if two variables are closely correlated, then we can predict one variable from the other. Do you agree or not?
Yes. Yes, we agree.
Okay, so correlation plays a vital role in locating actually the important variable on which other variables depends on. Okay, so if we have proper correlation analysis, we can have a better understanding of the data. Yes? Okay, so I was saying that if we have proper correlation analysis, we can have a better understanding of our data. Okay, so
Yes.
there are two types of correlation. I don't know if you know them: positive correlation and negative correlation. Did you hear of them?
Yes.
Okay, what is positive correlation, please?
Positive is when they tend to be more closer, and they are. It's like if one exists, the other will exist, and if it's negative, it's the opposite.
Perfect. Yes. Yes, exactly. So, positive correlation, as you said, is when we have two variables or two features that are positively correlated with each other. It just means that when the value of one variable increase, then the value of the other variable also increase, as you mentioned. And in the negative correlation, it means that when the value of one variable increase, then the value of the other variable decrease. So it's the opposite. So what we do actually in the filter method is that we drop variables that have very correlation with the target. Now remember when I was talking about supervised and unsupervised methods, I was saying that in unsupervised methods, we don't actually care about the correlation with the target variable. Instead, here in the filter method, in supervised method, we drop the variables that have a very low correlation with the target. Okay, so this is the filter method. So if a variable has a very low correlation with the target, it's not going to be useful for the model prediction. And so we drop it, we don't need it.
Okay.
Okay. Now we have another method or another technique, which is wrapper. A wrapper feature selection method, it creates many models with different subsets of input features and then select those features that result in or that gives the best performing model according to a performance metric. Okay, so what we do actually is that it's like testing. We test different models and we have, for example, subset of features of input features. We choose those number of features to begin with as the first model, and then we choose another type, another features for the second model, etc. And we test those model, and we see what is the best performance, what is the best performing model. And according to the best performing model, based on, for example, the accuracy, let's say, we're going to choose that set of features. Okay, remember we are talking about feature selection method, so we are trying to select the valuable features. Okay, so this is how the wrapper method works. And common methods of wrapper is recursive feature elimination, RFE. You can look at it for further reading. You can look at it in Google, so you can try to actually understand the concept of RFE. But RFE is a good example of wrapper feature selection method. It does the same thing as I mentioned before. So it creates many models with different subsets of input features, and then it selects the best features based on the best performing model. Is it clear?
Yeah.
Okay, so can someone tell me what is a filter and what is wrapper?
Filtering is to. Oh, I think Christabel was going to participate. Sorry.
Okay,
Yes?
the filter it looks for positive and negative correlations. However, the wrapper tries to create subsets and according to a combination of features, it predicts with scores.
Okay, so I think the wrapper definition is good, but the first one, can you repeat the first one? The filter?
That it okay, so it looks for positive and negative correlations between features
Between features? Just between features?
and
And
attributes.
between in a,
Yes?
and the variable,
The target.
the target, sorry.
Yeah, exactly. So it's actually see the target variable, and it drops the variables that are very low correlation with the target. Okay,
Okay.
perfect. So this is how it filters the features. So it goes to see the correlation matrix, and then it drops the variables that have a very low correlation with the target.
Okay, I see. Yeah.
Now for the wrapper, as you mentioned, we have it creates many models, different models, and then with subsets, of course, with different subsets of input features, and then it choose the best performing model. And then the best performing model is or the best performing features are going to be the selected features. Okay.
Yes.
Okay, so I guess it's clear. Now the embedded, the last one, there are here when we're talking about embedded, which is the last one, there are some machine learning algorithms that perform feature selection automatically as a part of the learning, as a part of learning the model. Do you know any machine learning algorithms? Can you tell me any machine learning algorithms do you know?
Deep learning.
No, it's not a machine learning algorithm. Deep learning is actually a subfield in machine learning.
BERT?
Okay. No, BERT is actually CNN. It's a neural network that we use in text. So it has nothing to do with machine learning algorithms. I'm talking about, remember when we talked about machine learning, we said that deep learning is a subfield.
Yeah.
All what you mentioned are in deep learning, okay? But machine learning has not only the deep learning as a subfield, but there are another subfield, for example, traditional algorithms, machine learning
Decision
algorithms,
decision
linear
tree.
decision
Classification
tree,
algorithms.
yes, random forest, linear regression, lasso regression, ridge regression, polynomial regression, logistic regression. All of these are actually machine learning algorithms.
Okay.
Okay.
Naive Bayes. Um, we also, what else?
K nearest
Yes,
neighbor.
exactly. So there are a
SVM.
lot of algorithms. Yes, exactly. Yes. So there are a lot of algorithms in machine learning. So this is what I mean by machine learning algorithms. Okay. There are some algorithms in machine learning that perform feature selection automatically as a part of the learning model. For example, decision tree or a random forest, actually, or lasso regression, ridge regression, are some of the machine learning algorithms that does feature selection automatically without we don't have to do this we don't have to do this. Okay.
Okay.
So that's why actually what that explains why they are so resistant to overfitting. Okay, for example, random forests are one of the best algorithms, machine learning algorithms, and it gives the best results, mostly with any type of data I've encountered. But that's just a general conclusion about random forest, for example, or decision tree. So it gives great results generally. And so one of the reasons why is not just the type of the data, but also because the feature selection is a part of the learning model, is a part of that algorithm, which helps maximize the accuracy. Okay, so okay, so now we finished the, I guess, the feature selection methods. So we have embedded, we have filter, and we have also wrapper as supervised. What about unsupervised? What did we say about unsupervised methods in feature
And
selection?
in supervised, we ignore the goal or the variable.
And
Yes.
we are looking for similarities to create clusters.
Yes, and how do we do feature selection when we are talking about clustering, for example?
Looking for similarities.
No, we use correlation actually. We use correlation for unsupervised learning. True. Remember when we talked about filter in supervised learning, we said that we drop the values that or the variables that have a low correlation with the target. Remember? Yes?
Yes. Yes.
Okay, so now in unsupervised learning, we don't care about the target variable because we don't have a target variable in
Yes.
unsupervised
Correct.
learning. Okay, so what we do is that we see the correlation matrix of the features that we have, and the features that add the same information to the model, we drop one of the feature, one of them. Okay, so we see that if two variables are highly correlated with each other, and that means that they add the same information to the model. There is nothing new. So we drop one feature and we keep the other. Is that clear?
Yes.
Yes, yes.
Yes, it's sometimes when I try to say the definition, I think I don't use the correct vocabulary, but yeah, I'm getting
Okay,
there.
okay, that's good. That's good. So yeah, I think we finished about feature selection methods. Now, if I asked you what is the method that we used for is if you give me a popular method that we use for filter. We mentioned the one method. These type of questions you can have them in the certificate, so you have to remember the names of the algorithms.
Um, is that the
T square,
recursive feature
Filter.
elimination?
T square,
Square?
Square.
T square
T square? No, no,
for filtering.
no. For filter, for the filter method.
Oh, well, chi square coefficient?
No, we
No?
mentioned just one.
Hmm. Pearson?
No, I'll go back so you can see it. For okay, so for the wrapper, I mean, for the
Oh,
wrapper.
our
Okay,
recursive feature
yes,
elimination?
recursive feature elimination. What about the embedded? Can you give me some algorithms that have the embedded?
The laser regression,
Okay, another one.
rich
Random forest.
regression.
Uh, okay, decision tree and then the forest. Okay, so perfect. So now this is the overall procedure of building a model. We after collecting the data, we divide the data into training set, test set, and validation sets. Then we do the model training. So we use the data that has been cleaned up and feature engineer to train the model. After that, we verify the model. So using uh, using actually a validation technique. And then after that, we fine tune the model. What does mean fine tuning the model? Do you have any idea?
Fine tuning? Could it be adjusting?
Yes, adjusting the parameters of the model. Remember when we were talking about the learning algorithm, and I mentioned that while learning, how the model actually learn is that it adjusts its parameters that we call hyperparameters. Okay, to actually learn. Okay, so fine tuning, it just means that we have to update the hyperparameters and adjust them, and then we test. Okay, and we see the performance. Now after that we have the model deployment, and of course we test the model in a real environment. So these are the steps to build your model. Now examples of supervised learning phase. Use the classification model to predict whether a person is a basketball player. Okay, so can you give me here what are the features and what is the target variable? And what is the type of the type of problem where we are actually trying to solve? Is it a classification or regression?
Regression problem?
Classification.
It's classification.
Why is it regression? Whomever said regression? Who said regression? Can you please tell me why do you think it is regression?
Because we are trying to predict if a person plays basketball.
Okay. Are we trying to predict a value?
No, we are just saying if a person plays basketball or doesn't play basketball.
Exactly. So if we are trying to predict a value, then we are talking about regression. Okay. But if we are talking about just two different classes or two different categories or more, then we are talking about classification. Is it clear?
Yes, thank you.
Okay. So what are the features?
The city and the age of the person.
I
Okay.
have a question. Why name isn't a feature?
Yeah, exactly. That was my question
Oh,
because she said
sorry. I don't know.
city.
I don't know the answer.
She said city and she said age as the features. Okay, and why not a name? Because simply because if you want to predict if a person or to classify as a person if a person is a basketball player, do you really need the name of the person?
No, you don't need it, right?
Exactly. So you don't need the
I
name
don't
of
know.
you don't need
Why
the
would
name.
you need the city? I can't understand that.
You cannot understand why they need the city.
Yeah, but
Maybe
not the
because
name. I don't know.
okay, maybe because okay, I can see that. I can see that because um maybe the city explains why maybe there are certain regions that they
Oh,
can
yeah, yeah,
actually
right. Yes,
play
yes. For
basketball.
example, in my
Okay.
city, there's no one who plays basketball here. Yeah, I
Okay.
understand. Yeah, yeah.
So what city are you in?
Oh, I live in a small city in Argentina. It's a
Okay, in
really tiny
Argentina.
city near a big city.
I only know Lionel Messi in Argentina.
Oh, well, he's from near my city.
Okay, nice, nice.
Nice.
Okay, so I was saying that maybe this is a valuable feature in their case to know if the person is a basketball player, and of course the age is a big one. And so the label or the target variable is yes or no. Okay, so this is a classification model to predict if person is a basketball player using two features. Okay, now the prediction phase. Now, if they give you the prediction phase is when we test the model. So we give it our new data, for example, Marine Miami 45, and we're trying to predict the unknown data. So we are trying to predict if she is a basketball player or not. Okay, and for example here they give you if city is Miami, then the probability is 7%, and here the probability is 70%, 20%, and yeah. So this is uh, the prediction data after for this and after giving it the new data. Okay, how can we measure is if our model is good or not? There is a generalization. There are metrics that we've mentioned before: the accuracy, the loss function. The loss function, actually, we see the validation loss and we see the training loss, and we can actually conclude from there that our model is have a better generalization or not. Okay, so we can see also the interpretability. Is the prediction results easy to interpret? We can see the prediction speed. How long does it take to predict each piece of data? In which case do you think we need speed? Can you give me an application, for example, where speed is so important?
Stock market.
Voice recognition.
Voice recognition, that's a okay, it's a big I need something specific that actually shows the importance of speed.
Chatbots.
Chatbots. We don't really need speed in chatbots. There are chatbots that you can actually text and they just
WhatsApp or send
yes.
a video friend.
I don't I didn't hear you. Sorry.
Tesla cars?
Self-driving cars.
Tesla cars, yes. Like Elon
Yes,
Musk.
exactly. So self-driving cars are they need speed, of course, because the reaction should be so fast. The prediction should be so fast. So there is like milliseconds of time to actually do to actually predict. Okay, so for example, we also need let's say in drones. Do you know what is a drone?
Yes.
Okay, so in drones, for example, when it flies, there are a lot of objects or obstacles that can come across the way. For example, birds, it can be buildings, etc. So it has to, and with the speed that a drone actually run, it needs to predict and see the object and see the obstacle and then move away. Okay, so in it's a decision that should be made in milliseconds, in a very short time. Also, I'll give you another example. You know, in healthcare, there are multiple applications in surgery. So there are some doctors that actually do surgery online with another doctor. Okay, so they just give experience to another doctor through online in a surgery, doing surgery. So the time here is actually so important. Okay, did you get the importance of prediction speed?
Yeah, it's for safety.
Exactly. So that's crucial. Another thing is practicability. Is the prediction rate still acceptable when the service volume increase with a huge data volume? So here we're talking about performance. So when, for example, we have a lot of service on that, or we have a huge number of requests uh, to that server, is the server allowed to actually support that or not? So this is how we measure a good model. Now we will remember the term generalization capability. We're going to talk about it in just in the next slides. Okay, so generalization capability. So now, okay, I will go back. Okay. Now what we do is actually we in to form a problem, or to form a problem hypothesis, all possible functions constitute a space, which is hypothesis space. The problem of machine learning in general is to actually search for a suitable fitting function in a hypothesis space. Okay? Remember that G function that should approximate the F function? Okay? So we are trying to actually search for a suitable fitting function in that hypothesis space that we created. So when our system learns from the training data too well and does poorly or badly when presented with new data, we say that it is overfitting. Okay, so when it doesn't learn well enough from the training data and it does actually poorly when presented with new data, we say that it is underfitting. Okay, so now do you understand the difference between the two now, or should I elaborate?
Could you please repeat the last one?
Okay, so remember, I will give you an example. So remember when you were training the model of the digits, right?
Yes.
There was a training loss, and there was a validation loss, and there was validation accuracy and training accuracy. So the training accuracy is the accuracy on the training set. The validation accuracy is the validation or the accuracy on the validation set. Now, when overfitting occurs, when we have high, for example, we have high accuracy in training accuracy. Okay, it is very high, but in validation accuracy, it is very low. So the model does poorly on the new data, okay, or on the test data, okay. Can you see my point?
Yes, yeah, I think so. Yes.
Okay, so this is a problem of generalization. So the model cannot generalize to new data, to new samples. It learns well just the images that we provided, okay, in the training. But when we were testing the model, the test accuracy is actually that is poor or it's bad. Now the underfitting is when the model actually can't learn. It can't learn, so the training accuracy is actually bad, and the validation accuracy or the testing accuracy is poor. Okay, so we have it cannot train, and it cannot train, or the accuracy of the training is low, and also um, the accuracy of on the new data is also low. So this is underfitting. Okay.
Yes, thank you.
Okay, so I'll give you an example. So we'll approach our discussion of overfitting with a metaphor. Okay, so let's suppose we've been invited to a wedding, so where we know almost nobody. Of course, the course of the afternoon we drift through okay, so the course of the afternoon we've drift through the guests. So you're going to, for example, to introduce yourself to the guests, and you'll meet new people. You'll have small talks, etc. So we've decided, for example, to make an effort to remember people's name. So each time we meet someone, we make up some kind of mental association between their appearance and their name. Okay, so suppose I meet one of you, for example. So suppose we meet someone named Fatima, okay? Or let's say Nick, okay, who has a big mustache. So we make a mental picture of Nick as a as a as a mustache, okay, and we try to make that picture stick in our minds. So later, when we meet someone named Erin, for example, and we notice she's wearing beautiful earrings, we make a mental picture of her earrings that have been shortened in one direction. So earrings become Erin, mustache become Nick. Okay. Now we make a similar mental image to everyone we meet. The day goes on, for example, and the wedding goes great, and at the reception afterwards, we bump into or maybe meet someone with a big mustache. We smile and we say, "Hi again, Nick." Now, only to get a confused expression, "This is Bob," so someone we haven't met before. The same thing can happen repeatedly. So we might be introduced to someone with beautiful earrings, and we thought this is what's the name I said before?
Erin, I think. Erin.
No, I said
Oh,
uh, we have the one with the mustache and the
Nick and Bob.
earrings.
Nickable,
Okay.
yes.
Exactly, exactly. So Erin is with the earrings. So now when we meet someone with beautiful earrings, we're going to say this is Erin, but this is Suzanne, not Erin. Okay. So the problem is that our mental pictures has misled us. So it's not we didn't learn people's name properly because we did. We just learned them in a way that didn't generalized when we met more people. So to associate someone's appearance with their name, we need some kind of connection between the two ideas. The more robust that connection, the better we can be at recognizing someone in a new context. Even if they're wearing a hat or glasses or something else that actually change their appearance. So in the case of our party or of the wedding, we learned people's name by connecting them to a single feature. So the problem is that when we meet someone else with the same feature, we had no way to tell us that this was someone new. Okay? So did you understand the problem of overfitting?
Yes, it was really, really
Yes.
clear.
Okay, so this is the problem of overfitting. And underfitting, as I mentioned before, is it does poorly on both on the training and on the validation set, on the test set. Okay, now let's move on. I guess I can't. Okay, I will stop sharing again. I guess I can't. Now you can see, I guess, right? Can you see my screen, right?
Yes.
Okay, perfect. So I guess this is the last slide. So we're going, as I said, divide the machine learning into two parts. Into validity, until the model validity, and the next session is going to be the part two of machine learning overview, because there are a lot of concepts and I didn't want to actually give it all away at the same time. So I will give you an exercise to actually practice and to actually revise a little bit of time to actually revise what we've gone through. So back to the model validity. So, as we mentioned before, the central challenge in machine learning is that our algorithm must perform well on new, previously unseen inputs, not just those on which our model was trained. So, the ability to perform well on unobserved inputs is called generalization. So we can control whether a model is more likely to overfit or underfit by altering its capacity. Remember, we were talking about generalization capacity. So it depends on the capacity of the model. We have to, what I mean by a model capacity is its ability to fit a wide variety of functions. So models with low capacity, they may struggle to fit the training set. But models with high capacity, they can overfit by memorizing properties of the training set that do not serve them well on the test set. Remember the analogy of the within? Okay. So one way to control actually the capacity of a learning algorithm is by choosing the hypothesis space. And what I mean by the hypothesis space is the set of functions that the learning algorithm is allowed to select as being the solution. Okay. So let's give it an example. For example, in this picture, we have three images, and we have underfitting. Not all features are learned, as you can see, because there are a lot of features that we didn't learn. We have overfitting. Let's see the extreme. Overfitting noises are learned. So here, as you can see, the model is trying uh, to actually get all of the points. So back to the person, I guess I don't remember the name, who actually got the loss function in the exercise, the last exercise, a low loss function. Do you remember? Who
I
is she?
think it was me. You're talking about me, I think it.
Yes, yeah,
Yes.
exactly. So when for example we had linear regression model and it didn't fit the model well, okay, didn't fit the points well. You were talking about quadratic, right? Or polynomial?
Yes. Polynomial, yes.
Yes, polynomial. So here going from here, ax plus b. Do you know the function of a linear regression?
Which function?
Equation, the equation of linear regression. Y um, ax plus b.
Oh, then just the yes, the linear function. Yes.
Yes, exactly. So linear function ax plus b. Now, when we're talking about polynomial, we have to, for example, if we're talking about polynomial with a degree of 9, we have a more complex model. Okay, so as long as we are trying um, to actually increase the degree of the x or the degree of the polynomial function, as long as we have a more complex model, okay, and we are going to overfit in. Can you see my point?
Yes, yes. I think that the one that was the best was the quadratic one because of
Yes.
the error, which is quadratic.
Yes, and each model has its capacity, as I mentioned. So
Yeah.
the capacity of the model is just the ability to fit a wide variety of functions. So models, as I said, that with low capacity, they may struggle to fit the training set, and models with high capacity, they can overfit by memorizing properties of the training set. For example, in the last example. So how can we control this capacity? Um, you can let me see my phone. Okay, so how can we control this capacity of the model? One way to control the capacity of the model is by choosing the hypothesis space. And for example, the linear regression algorithm has the set of all linear functions of its input as its hypothesis space. So we can generalize linear regression to include polynomials rather than just linear functions. in this hypothesis space. So this is doing so, it will increase the model's capacity. Okay, so going from the linear regression model to polynomial regression, for example, we're going to polynomial function, we're going to actually increase this model capacity. I think this is it's going to be hard for people who didn't have a who doesn't have a background who don't have a background on mathematics, but this is just a deep look into what is really overfitting and what is underfitting, explaining it in a very mathematical way. But the general idea, as I mentioned before, if you took the example of the within, you can have just the general idea of what is overfitting and what is underfitting. Okay, so just one thing I want to mention is that the machine learning algorithms will generally perform best when their capacity is appropriate for the true complexity of the task they need to perform, and also the amount of training data they are provided with. Okay, so mostly we fall into the trap of underfitting when we have a small amount of data. Okay, so it's like the capacity of the model is bigger than the provided data. So that's why we fall into we fall into the underfitting problem. And models with insufficient or insufficient capacity are unable to solve actually complex tasks. So models with high capacity can solve complex tasks, but when their capacity is higher than needed to solve the present task, they might overfit. Okay, so do you understand what is the concept of capacity, generalization capacity, and how it is related to underfitting and overfitting?
Yes, it's clear.
Okay, so do you have any questions about that?
No.
Okay, so I think we finished the course. I have just some few things to mention. I will send you an exercise in the WhatsApp group, so I hope everyone is there. Did everyone join the group? Can you please resend whomever have the link of the WhatsApp group? Can you please resend it on the chat so for people who actually did not join, so they can join?
Okay.
2 people
Okay.
in the group, so I think almost everyone is there.
Okay, perfect. So can you please, all of you, write your name and present, okay? So just for the absence. Thank you, Christabel. Okay. Anna Caroline, Berkey. We have, okay, Arshna, Elizabeth, Sharon, Angina, Maria Camila Perdomo, Zaira, Zaira Martinez, Cheryl, Alumno, Maritza, Arena, Erika, In the meantime, people who actually wrote their name, they can go back to the course and take the survey. Okay. People who actually joined or enrolled into the course, please go back and take the survey. Also, just a quick look on the exercise that I'm going to send you. Okay. So this is going to be the exercise about image classification of an American Sign Language dataset. Okay, so this okay, so if we type American language, just to see just an overview. So this is can you see my screen? Can you see the image?
Yes.
Okay, so this is actually the American Sign Language recognition and the images that you have. So the task is you're going to do a classifier, okay? So it's actually kind of the same as the other one we've took the notebook of MNIST. So it's the same but with signs. So but here the difference is that you have 26 letters, and also this dataset is from Kaggle. You have to load the data, you have to read the data in CSV format. So I actually wrote the code for you here. So and I explained everything in the comments for you to understand. So here we have a CSV for the training data and CSV for the validation data. Here just to actually see the head. And yeah, so you will find here some exercises to do. So here in the exercise, you normalize the image data. Remember when we did the normalization? So to do, you have to normalize xtrain and xvalid, as we did last time. This is the solution. Try not to look at it before, so you have to do it and then look at it. So if you're stuck. Okay, so here you can have to categorize the labels as we did with the last data set. So you have 24 categories to do, and here you can write your code. If you're stuck, you can see the solution, but try not to actually um, memorize the steps. Then we have to build the model. Here I explained what I want to build. So here, for example, the input layer is going to be containing 512 neurons with this activation function and the expected input images, sorry, with a shape of 784. So here, everything is explained and you have to define the model. Of course, there is a solution that you can look up to. And here you fit the model, so you have to do this to actually write the comment for fitting the model. And okay, so afterwards I did some. There's someone. Okay, admit it. So afterward, there is someone. There is a. Sorry, there is a discussion. This I gave you a question and I answered that questions. Just so if you have any questions about that, you can send it into the WhatsApp group. Okay, so try to do this exercise in your free time, and of course, if you have any questions, I'll be happy to help. So I will share with you the link, and you can find it also in the WhatsApp group. Okay, perfect. Did you get it? Okay, Bitsabe, yes, I was sharing my screen. Just I wanted to show you the exercise that we're going to do. And now this is the link, so you can look at it up afterwards. Okay. Okay, guys, did you actually took the survey?
It's the one that we did yesterday, right?
Yes. Cristabel, I didn't hear you.
It's the one that we did yesterday.
Yes, it's the same. Can you please go back to the website and do it?
We have to
It
do that.
says you have completed the survey and no need to answer.
Okay, so is it just for one time?
Yes, that's what I'm getting. You have completed the survey and no need to answer.
Okay, so I will see if I don't know if it's just for one time or for every session, but Fernando, are you here? Okay, so I guess he's not here. Okay. Okay, I will see and I will let you know if you have to take it again or not. Okay?
Okay.
Okay, perfect. So, Erika, I got this message when trying to open the collab exercise. You need access. Okay, I think I shared it with everyone. Get link, only people added can open with this link. So, okay, so I guess it's this. I will do the editor and share with you the link. Okay, perfect. Okay, can you check now?
Thank you. Now it works.
Now it works. Okay, so you can actually do this. I will show you. Okay, so you can actually create your own copy. So we can go here into file. Can you see? And then you can save a copy in your drive or something, and we'll open up a version, a new version, so you can have your own file. Okay, because in this way I have shared with multiple people, so you might see that some people actually changed this or that. Okay, so you can save your own copy, and then you you modify what you have to modify. Okay.
Okay.
Is it clear?
Yes.
Okay, so you
Yeah.
have it here. Save a
I'm
copy in
sorry,
drive.
I didn't get the link.
I have just shared it.
Oh, okay, thank you.
Okay, so
I'll
you can.
wait.
Okay. So everybody wrote his name with present, right?
Yes.
I did, but I'm not getting messages, so I don't know if you're getting my messages.
Yes, yes. I can, okay, so I can see. Can I have the link of the survey? Okay, so is anybody has the link of the, let's see if I can have it.
I put it in the chat.
Okay, perfect. Thank you so much. So you can actually go there and enroll into the class, and you have there take the survey, so you can take it. For people who didn't actually take it. Okay, so perfect. So please, if you have any questions, you can actually send them into the WhatsApp group, and we can discuss about this exercise in the WhatsApp group. If you actually have any remarks, comments, etc. So I'll be available and joinable into WhatsApp. Okay.
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 Okay. So next session is going to be a machine learning overview, the second part, and also deep learning overview if we had time to actually do it. So we will do both of them. So I think we will close this session for now, and we'll have next time we'll continue with the chapter 2. Okay.
Okay.
Okay. So have a nice evening,
Okay.
and see you soon. Thank you
you.
for being there.
Thank you.
Thanks.
Thank you
Good
so
night.
much.
You're
Good
welcome.
night.
Bye.
Good
Good
night.
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 Bye. Take
Bye.
care. Bye.
See you.
See you.
Okay, good night. Thank you, everyone.